Hi, we're CForce, and this is our Team Design Review video. I'm Audie.
I'm Olivia.
I'm Sydney.
And we're all we're all part of Lexington High School's all-girls robotics team.
The parody bits.
Okay, so first our smart requirements. So as an overview, the CubeSat system will be able to detect and analyze colored pieces of plastic. And this is mimicking pieces of plastic in the ocean. Even though our project won't be as large scale as going to the actual ocean, we hope to be able to achieve and be able to detect and send pictures of the pieces of plastic. And so the electrical power system will provide energy storage, power, and power distribution, source, regulation, and control. And this will provide at least 3.762 watts of energy consumption of the subsystems, which will later be covered by Sydney. And the CubeSat shall also capture pictures of colored plastic on a plane surface with 120p resolution. And the CubeSat shall transmit data to the ground station using Bluetooth for communication with a distance of about 25 feet. And this data will be passed at a data rate of about 1,200 bits per second with closure. And the camera resolution and data rate will be covered by Olivia later. So the ADS system shall contain IMU sensors that measure the attitude with respect to a coordinate system. And the sensor shall have reasonable sensitivity and precision in order to calculate determination and exact location. And the ground station will receive and process the images to generate information of plastic size and location, and also send the images and process information to GitHub. The structure system shall provide structure integrity to the whole CubeSat and also provide some thermal dissipation. And because of 1U satellite requirements, the CubeSat shall have mass less than 1.33 kilograms. Now for the concept of operations, when the CubeSat is first launched, it will be powered on, the IMU will be calibrated, and it will test the connection to the ground station. And then during its orbit, it will take pictures every 10 seconds, and then analyze the picture to find the colored plastic. And when it finds a colored plastic, it will crop the picture and keep track of size and location. Then it will compress and send the crop pictures to the ground station every minute during crossover. The ground station will receive the images, check the images, and then publish the finally processed images to GitHub.
This is our system level block diagram. It shows all of our subsystems. So under the structure subsystem, we have everything that holds our CubeSat together and provides it with structure and protection. Our aluminum corner rails, acrylic side panels, belt brackets, and nylon standoff, and screws and nuts. Then under our power subsystem, we have the solar panels, which charge the batteries, and the power meter, which will either be in between the batteries and the Raspberry Pi's electric power system or the solar panel in the batteries. Then in our command and data handling subsystem, we have our camera payload, which receives instructions from the Pi and also returns images to be sent to the ground station, as well as the IMU, which also receives instructions and returns data to be sent to the ground station as well.
So this is our CAD model. As you can see, it has all of the different components of the CubeSat except for the cables because it crowded the image and you weren't really able to see where everything was. But the cables will be able to run through the holes on the acrylic side panels, which are left open. As you can see, we have the battery pack, the Raspberry Pi, the IMU, and the camera all within the CubeSat, while the solar panels are on the outside, spread out so that they don't concentrate heat. I also kept them away from where most of the sensitive parts were, such as the camera and the IMU on one side of the CubeSat. And most of the more complicated pieces like the Raspberry Pi, I got from GrabCAD and then converted to be able to use in Fusion 360, while the rails and the acrylic side panels I created from the schematics that were given to us. So this is our mass budget and bill of materials. Our mass budget is based on the limit for what a CubeSat can be, which is 1.33 kilograms. And our cost budget is $300, which is based on the spreadsheet of parts that we were given. This is a list of our bill of materials with all of the different subsystems, such as the power subsystem, the camera and payload, the command and data handling subsystem, the cables, and the structuring connection subsystem.
This is our power budget. It shows what we'll be using the power, which is provided by our battery pack, which is charged by the solar panel. The power subsystem in all includes the battery pack, the solar panel, and the USB power meter. We tested each use case by making a sample program of what each operation may look like. So, for example, for the camera, we just did watched a voltage for as the camera took a 10-second video, which recording a video would likely be the maximum use case for the camera. So we monitored the average voltage over that time and the average amperage over that time, and then use that to calculate, well, not the average, the highest, sorry, and in order to calculate the peak power. No, I'm so sorry. Yeah, for voltage in the columns, well, both were calculated. In the columns are the average voltage and amperage, and I took the maximum values from that to calculate the peak power. All in all, we did this for each row and found the maximum use case as approximately 3.8 watts.
So first is the software architecture from the CubeSat's view. So first the CubeSat will be powered on, and then it will test the connection to the ground station and also calibrate the IMU. And then at this point, it's ready to start its orbit. So during its orbit, it starts taking pictures every 10 seconds. It will then process the image using OpenCV and crop the picture to only show plastic. And since the crop picture won't show the location and size of plastic, the location and size of plastic will be stored separately in a text file. And then every 60 seconds, the CubeSat will download the cropped images in the text file to the ground station. And then this will repeat for the orbit. And then after 5 minutes, the orbit will end. It will end its mission. And then it will wait for an end signal from the ground station. So from the ground station's perspective, it will be powered on. It will wait for a connection confirmation with the CubeSat, and then it will receive the photos in the text file. If something's wrong with the pictures, then it will request a full resolution backup picture from the CubeSat, and then it will reprocess and recrop the backup picture. And if the pictures are perfectly fine, then it continues on. And then the processed images are then pushed to GitHub, and then after the images are pushed, it will send an end signal to the CubeSat.
So this is our link budget. Our modulation technique is going to be quadrature phase shift key. The advantages of this is it has a higher data rate, it's more power efficient, and it's less susceptible to errors than ASK. The estimated data rate based on a 600 baud rate is 1,200 bits per second. Based on our SSI values and the SNR values, the distance has to be less than 25 feet or the link margin will be too small for the data to process properly. So our data budget is based on that 1,200 bits per second rate. So pictures will be taken every 10 seconds and downloaded after 1 minute. So we'll have 6 pictures in total. Our images will be cropped to only show pieces of plastic individually and also converted to black and white to save data space. And then those will be sent with the information in the text file of the location of the center of the image compared to the center of the original picture before it was cropped and the time taken. The ground station that can then use that information to find the exact location. Our passover window is going to be 5 to 10 minutes, which includes maybe extra processing time for the images, and then also transfer time, and then also time for us to request a full JPEG and be able to have it delivered to the ground station and then checked. And our full backup images will be saved for 3 orbits and then deleted after to be able to make space for new full backup images.
For integration, our camera and IMU will both be connected to the Raspberry Pi, which is powered by the battery bank. And the solar panel charges the battery bank and is connected through the USB. The aluminum corner rails and acrylic panels surround them and provide structure and fixture for the systems as they go about their operations. The USB power meter is not always connected, but occasionally would be either between the solar panel and battery, or battery and Raspberry Pi.
And then in order to make sure that everything's working for our final launch, we'll need to test different functions. So the first function that we'll need to test is if the camera can take pictures. And then second, you need to test if these pictures can be successfully transferred to the ground station. In addition to receiving pictures, we need to third test if the ground station can receive the attitude from the ADS IMU system. And then fourth, we'll need to test if pictures can be processed and in combination with key information, determine plastic size and location. And then fifth, we'll need to test if data is shared at GitHub.
Thank you for listening, and we look forward to your comments.